blade. It's a blade with a reinforcement in titanium, for example, on the leading edge, in order to increase the resistance against impact. And so you see that, in fact, behind this turbofan, that looks like extremely easy when you take the first drawing I gave today, you have a lot of complications. What is the real organization you have? Is it the 3-spool turboshaft? Is it the 2-spool turboshaft with a low-speed booster that will be limited in bypass ratio, so limited in decrease of the TSFC? Or do you need to invent a gearbox, very compact inside, which is the gear turbofan? A lot of complications. And on top of that, you will need to invent very special techniques to manufacture these fan blades. Very, very complex. If you need to develop a technique like this one, that must be certified, a technique like this one, that must be certified, you speak directly in billions of euro. Just to develop the technique needed to manufacture that. You have just manufactured fan blades, not the engine. You have invested billions of euro for that also, billions of euro. So very complex, and it takes a lot of time to develop. And so behind the fact that it looks like easy to build a turbofan, in fact it's very, very complex. The small historical fact that I'm always explaining is, if you take the PhD thesis of Sir Frank Whittle, I think it was at Cambridge University for sure, 1942-1943, he has already explained that the best cycle was the turbofan. He didn't want to make turbojet, but it was then absolutely impossible to make a turbofan, because mainly the materials and the manufacturing techniques were not available. Thermodynamically, he was indeed explaining, he is explaining that, he's dead now, he was explaining this cycle. Thermodynamics is not a problem, even for students. Thermodynamics is not a problem, they like thermodynamics. But the complexity is in the manufacturing, in the shaft, in the blades, in the bearings, in all these aspects. And that's why it took more than 20 years to build the first turbofan compared to the first turbojet. And even the gear turbofan, this is an engine of 2010, even after 2010. So you see, the first turbojet, 1950, so it took 60 years in order to build this one. Whereas the thermodynamics is easy, but to build it, it took 60 years, with, of course, thousands of engineers who worked in the development of the gear turbofan. But very interesting to see where are the challenges. The challenges are not in the computation, the challenges are not in the understanding of the physics, in the thermodynamics, in the values that you obtain by computations. No, the problem is in the manufacturing. Manufacturing, the materials, certification, and all these things. So, in order to explain you something, so you have here, this is quite heavy, a turbine disc. You see how the turbine blades are inserted in the disc. You see, in the disc you have small holes that have been made, and the turbine blades, they have the shape of what is called a pine tree, this is the inverse of a pine tree, because the pine tree is the top near the center. And each blade has this shape. And you need to make also this shape in the disc, of course. So you need to make all these holes in the disc, and then you put the blades like this. If you have a composite carbon-carbon blade, it has also this shape at the foot of the blade. And this foot of the blade is in composite material, but the disc is metallic. And you need to have then, and you will have then, contact composite metal. But the blade is moving, huh? When you have all these vibrations, all these changes of rotational speed, all the change of the pressure there compared to the pressure there, the blade is slightly moving like this, slightly moving like this, slightly moving like this, and you have a contact carbon metal, but the metal is much harder than the carbon. Or are you certifying that the lifetime here and the lifetime there of the carbon blades inside the metallic disc will be the same? Very complex problem. Also, in order to discuss a final point related to turbofans, we need, of course, to discuss of design. Of design. Of design. Of design, evolution, it is, let's say, all the same. All the same as what we have discussed until now. I will remember you mainly what we have discovered until now. A very important point is that the TSFC is decreasing thanks to the altitude. We will fly at high altitude. Roughly speaking, the beginning of the troposphere, the beginning of the tropopause, at 11 kilometers altitude, 36,000 feet. This is the same for a turbofan and a turbojet. The second point is the very bad effect of the flight speed. It has a very bad effect on the TSFC. I put two arrows there because this effect is larger than this one. But you want to fly fast. So this is what you will do. I remind you always that we have a problem with hot and high takeoff conditions. Takeoff conditions. This is not bad, not good. No? So we are seriously impacted by this situation. And then there is something else that I would really like to insist on. This is the evolution of the thrust, not the specific thrust, the thrust with VA. If you remember well, with the thrust of the turbojet, in function of VA, I'm speaking about subsonic applications. So let's say up to 0.8, in order maybe 0.82 or 84, I don't know, let's say around 0.8. What had I said? The turbojet, it was something like a constant thrust engine. In fact, it was not really constant. I remind you the equation of the thrust in a turbojet. This is this one. And we had explained this has a negative effect, the minus VA, it should decrease. But at a certain moment, it starts to increase, and it starts also to increase. And so it's going down due to the minus VA, and then at a certain moment it's stabilized because the minus VA is a negative effect, m dot is increasing, and at a certain moment Vjet is also increasing, and you have this compensation. In a turbofan, this is not at all like this. Why? Because you have m dot p and Vjet p in the thrust, and you have also m dot s and Vjet s minus VA. And so each time you have the minus VA that is playing a very important role, but mainly we have decreased the speeds here by a factor at least 2. And in fact, we are even decreasing or dividing by a value higher than 2 when you increase that for this that is equal. When you increase the bypass ratio, this speed is reduced. And because when you increase the bypass ratio, you are also decreasing the fan pressure ratio, this is also decreasing. And so what is the effect? You will start from a higher value. Because you have, at a certain bypass ratio, a higher thrust, but also you will have a much larger decrease of the thrust. So you have a higher starting value of the thrust, but a much larger decrease of the thrust. Why? Because this is much lower. And with a higher and higher bypass ratio, lower and lower and lower. And if you gain here 10%, it's 10% of a much lower value. When you were gaining 10% of 600 meters per second, you were gaining 60. But when you gain only 10% of only 300, you gain only 30 meters per second. And when it's 207, you gain only 27 meters per second. But the minus VA is still the same. And the minus VA is on both sides. And so you will have, in fact, a much larger decrease. And with the increase of the bypass ratio, what's happening? You will have, in fact, a higher and higher starting point, but a larger and larger decrease of the thrust with the flight speed. And this is a very important feature. This is a very important feature because it is changing totally the way the thrust can be used, will be exploited. You see, if you have the same aircraft, I know it's a comparison that is very dangerous, because you don't have the same engine. The engine is much larger, so the drag is not exactly the same. But let's say you have the same aircraft, flying at the same point, you must create the same thrust, because the same drag, you will have the same thrust. But when you take off, you have a much larger thrust. And so, what can you say? You can say, I will, in fact, if I have 2 times much thrust, instead of putting 4 engines at takeoff, I need only 2. And then you will take 2 engines instead of 4. Of course, maybe you will not have enough thrust when you are in cruise, but then you need to increase the level of the TIT. And so it is opening the large bypass ratio turbofan, the very large bypass ratio turbofan, is opening the door to 2 engines aircraft, twin engine aircraft, much more than 4 engines aircraft. The GE90, that has been the first very high bypass ratio engine with a bypass ratio around 10, has allowed